So now we're going to start talking about fluid flow and fluid dynamics, which is a very complicated subject. Fluid flow is very complex. So the first thing we're going to do is we're going to make some simplifying assumptions so that we can have a nice base where to start from. So for the next for this video and the next, we'll be talking about an ideal fluid. So we have ideal fluid flow. And what we mean by an ideal fluid is one, it's incompressible. So if it's incompressible, it cannot be compressed. So we can say that the density of the fluid remains constant. So density is equal to a constant. This actually works really well for fluids. Not so good for gases. I mean, if there's small pressure differences, then a gas will remain more or less at a constant density. But it works pretty well with fluids. Most fluids are pretty incompressible. So the density remains constant, so that its volume doesn't change a whole lot unless the mass changes. Also, it is inviscid. So inviscid means that it has no viscosity. So no viscosity. And viscosity is it's an internal friction. Viscosity means internal friction within a fluid. So there is no internal friction, is really what this means. You could think of something as like a syrup or molasses having a very high internal friction. It's very slow to pour out, so it has a high viscosity. This is basically like where early on, with when we were first learning about Newton's laws, we might have assumed that there was no friction at first, or maybe with the work energy theorem, we assumed there was no friction. It's a similar thing. So we say no viscosity is no internal friction. And we also say that it's steady flow, meaning that the flow does not change in time. It's a constant flow. It's not changing throughout time. We actually have, let's say we have, a pipeline. Let's say I'll draw another pipeline here, and we have some fluid flowing through it. We call these blue lines, these are flow lines, and this is a path a particle takes. And what we mean by a steady flow is that the particles don't deviate from this path over time. So if we look at it now and we look at it 10 minutes later, the particles would still be continuing the same path. Another thing with these flow lines really quickly is that if we put more of them together, this would not be very accurate for this pipeline, but if a bunch of them are grouped together, it means that the flow is faster. So this actually represents, as far as flow lines go, this represents a faster flow than this does down there, the tighter that are grouped together, which will be important in the next video. So this is an ideal fluid. It's incompressible, it's inviscid, and it flows at a steady rate in time. It's not changing around. Okay, so now next thing, let's define this flow rate. So let's say we have a certain amount of time. We have a pipe here, and we have a chunk of a fluid flowing through it. Now this fluid has some area to it, and then it passes through this distance in this much time. And it passes through at an average velocity or average speed of v bar here. So v bar is going to be the distance it travels divided by that time. Just the definition of average speed, distance over time. If we take and we were to multiply this distance over time times area, so distance over time times the area, well then distance times area, this would give us the volume. This would give us the volume at which it travels. So this is the volume per time, which is what we have here. Distance times time, which is this is the speed, times the area is equal to the volume per time. So we use Q to denote this is the volumetric flow rate. So the rate at which fluid flows through this pipe, Q, is equal to the area of the pipe times the speed at which it flows through, the average velocity. Okay, so that would be, this is our volumetric flow rate. If we wanted a mass flow rate, we would actually just multiply it by the density, and we would have a mass flow rate. Okay, so volumetric, this is volumetric flow rate. I guess the mass flow rate, if we wanted to say here, mass flow rate would be equal to the density times the volumetric flow rate, which would, this is density times area times the speed here. It would give us the mass flow rate. So with this, we have a relationship here between the mass flow rate and the volumetric flow rate, which is very obvious. So let's say that we have another pipe that reaches a constriction. So let's say, it's area 1 is much larger here than, we have area 1 over here, which is larger than area 2. It reaches a constriction right here in the pipe. And so it was traveling at some speed v1 before, and meaning that some volume, this would be volume 1, would pass through in this time. This is our flow rate q1, which would be equal to area 1 times velocity 1. Okay, so once it reaches this constriction, something must happen. Since the area gets smaller, something needs to happen to the velocity. And this is really related to, it's actually a statement of conservation of mass. Mass isn't created or destroyed, it just changes forms. And so we can't lose any mass, we can't gain any mass either. And so our mass flow rate must be the same in case 1 as it is in case 2, so therefore our volumetric flow rates have to be the same as well. Q1 must equal Q2. And since our volumetric flow rate is area times velocity, we must have here area 1 times velocity 1 is equal to area 2 times velocity 2. So this is what we call the continuity equation, or equation of continuity. Which is really straightforward. It's just a statement of conservation of mass. It says that whatever flow rate we have in one section must be the same as it is in the other section, as long as, and the key for this one is really that it's incompressible. It can't be compressible for this.